Hello, thanks for joining us today. We're going to continue our discussion of Chapter 7 with Lesson 2, Differentiating and Integrating Exponential Functions, or the day your life changed forever. Now, I'll explain mine in a second. Let's use the calculator to experiment a bit. We're going to graph second e to the x, that's the natural log button, and then the derivative in the same spot. So if it's been a while since you've actually used your calculator to do a derivative, or the graph of a derivative, you stay in the y equals menu, math, 8 for derivative, we differentiate with respect to x. Who are we differentiating? Alpha trace y1. And where are we differentiating? Everywhere. Which x value? All the x values. So it's going to graph y1, the original function in blue, and it's going to graph y2, the derivative of the blue guy in red. Zoom 6 to make sure we're all looking at the same thing. What? See, I almost wish I had the slower emulator now. So what happened there? The blue completely changed to red. Here is it in instant replay. Okay, that was slower. I don't know why. See? Wow, you should say. So it turns out that E, Euler's number, is the only base for where the basic exponential function and the derivative are the same. E is its own derivative. E to the x is its own derivative. And this is a magical, phenomenal property. It's the only function in the world, or the only interesting function. 0 is the same one, but boring. So, e to the x, its derivative is e to the x. The slope anywhere on the exponential function is whatever that value is. Interesting. These two forms are going to be boxed in red. These two forms are the only ones you have to know. Technically, this one, this is for any other base. If you just use this one for e, it would say that the derivative with respect to x of e to the u equals e to the u times u prime times natural log of e. Natural log of e is just 1. So that's why this formula is the only one you technically have to know. But this formula comes up so frequently that you should memorize this one. All you need are these two. These are just the non-chain rule versions of these. So we're going to take e, copy it, and then multiply by the derivative of the exponent. So u prime becomes the derivative of the exponent in this case. U prime, the hook-on factor, is the derivative of the exponent in this case. That's the input. It's the same chain rule version that we've been doing, where the derivative of f of g of x, I'm going to write this down many times. We take the derivative of the original function, keeping the inside the same, and we multiply by the derivative of the input. For e, the input is the exponent. The derivative of the original function is the same. That's why we have that first copy. Right? Basically copy it. but take the derivative of the outside. Oh, wait, but the derivative of e is e. And then multiply by the derivative of the inside. And the inside is the exponent. That's the idea. Maybe it'll make more sense in practice. So, here we go. We have y equals blah. So, the derivative, dy dx, we'll start by keeping a direct copy of what came before. And then I'll say, okay, what's the inside of e? Well, it's the exponent, so we'll multiply by the derivative of the exponent. What's the derivative of x squared minus 3x? If you said or thought 2x minus 3, you are correct. And that's it. Isn't that cool? Isn't that amazing? That's it. Now you're differentiating e. All right, so if we're eventually going to have to differentiate the exponent, it might be helpful to rewrite, just like in the old times, but this time the exponents first. So for instance, on this one, it might be helpful to notice that's e to the negative 3t to the negative 1 power, since we're going to have to differentiate it. So that makes g prime of t equal to, notice I took the derivative of the left-hand side also, and we're going to copy that word for word, 3t to the negative 1 power. That's t to the negative 1, not t minus 1. And then I'm going to multiply the whole thing by the derivative of this. Bring the power down. Negative 3 times negative 1 is positive 3. T, negative 1, subtract 1. We're differentiating. And you're done. Oops. That's it. We're going to rewrite that power first. What's the square root power? Oops. 3 to the v to the 1 half. F prime of v equals, copy everything down, same power and everything. And now we're going to do two things that we haven't done before. So, the derivative of 3 to the u, just to be clear here, what this is saying is the derivative of 3 to the x equals 3 to the x, and this is kind of like a hook on, natural log of 3. That's this rule in practice. A is just going to be some constant. So the derivative of phi to the x, just to use this rule one more time, because we did phi to the x in the last lesson, would be phi to the x, keep it the same, and then multiply by the hook on. The hook on for exponentials. So, keep it the same, times natural log 3 times the derivative of the power. Move everything over just a smidgen, shrink it just a bit. Now the derivative of v to the 1 half would be 1 half v to the negative 1 half. And that's it. We did the derivative of the exponent. Derivative of the exponent. I'll tell you at this point that if you want to be really good at calculus, if you want to get a 5, you want to have time to check all your answers on all the tests, you're going to memorize 2 basic rules. Really helpful. That the derivative of the square root of u equals 1 over 2 root u, u prime over 2 root u. You'd also be really benefited by doing this one. The derivative of 1 over u is negative u prime over u squared. These two come up so often that they're really helpful. They're both just power rules. They're both power rules, but they're power rules that people screw up. Right? And as soon as I saw this one as negative 3 to the negative t power, a student who has this memorized could be as graceful as this. Oh, the e rule. So copy it. Multiply by the derivative of negative 3 over t. So that's negative 3 squared. Make it negative. Negative 3. The derivative of t is just 1. Okay. Over here, keep it the same. Multiply natural log 3 because it's 3 times 1 over 2 root v. Okay? It helps you. It's faster. Sometimes you only see these forms, so you'd have to simplify all that. Again, kind of annoying. Last, for this video, find the relative extrema of this. Points. No calculator. In fact, for the homework, I'm going to advocate again, make sure you're not using your calculator. That'd be pretty stupid. The whole point is that we're not using our calculators right now. The words relative extrema should make you think of one thing. How do we find relative extrema in calculus? 3, 2, 1. The way we find relative extrema is a first derivative num line. And if that doesn't ring a bell, the word's first derivative should. So we're going to find the derivative of f. So we're going to do this as a product rule. Product rule. Ooh, something we mess up a lot on the tests. First times the derivative of the second. So here's how I'm seeing them broken up, like that. The derivative of this guy, I would keep it the same. And then I would multiply by the derivative of the exponent. What's the derivative of what's the derivative of negative 2x squared? Oh, it's negative 4x. Plus the second guy times the derivative of the first. For these problems, and for a lot of first derivative number line problems, we want to factor. Factoring usually helps clean up things. So we're going to factor it. F prime of x. Who do we see in common? Well, I see both factors have e to the negative 2x squared. What would be left over? Negative x times negative 4x. And over here, 1 times negative 1. Okay. It's not just gone It's 1 times negative 1. Like this should really be negative x times 1 times, okay? It's really frustrating. We're going to keep trying to factor it. We'll keep trying to simplify. 4x squared minus 1. The next thing we do, well, let me pick my colors. Find critical numbers. Okay. F prime of x is equal to 0. That's one thing we check. And here's again where it's important. E to the x equals 0? Never. It's not possible. E to anything will never be 0. So what we're left with is 4x squared minus 1 equals 0. 4x squared equals 1. X squared equals 1/4. I will shrink it. And then we're left with x equals 1/2 and negative 1/2. I took the square root of both sides. F prime of x undefined. Well, is this one ever undefined? No. That's another really important thing you have to know about e to the x. It's a nice function. It's a beautiful function that's always continuous and whose domain is all real numbers. And this guy's totally fine as well. So we only have those two critical numbers. And if you forgot all of this, you have not been doing your homework, which is bad. We make an f prime number line. Domain's all real numbers, so we have arrows on both sides. We'll put both critical numbers on here. And now we test points. When we test values, do we test in f or f prime? If you center the f prime, good, because it's an f prime number line. All right, so 0. What do we got? E is always positive. So that guy is always positive. That's why it can never equal 0. It never crosses 0, it never touches 0. It gets really close, but it never gets there. Positive e to the any power is always positive. It depends on its coefficient. The coefficient's 1, but the guy by itself is always positive, like we talked about in the last video. So what really matters is the sign here. 0 is easy to test anyway. E to the 0 is 1. 4 times 0 squared, 0. 0 minus 1, negative 1. So we're talking about negative. Don't assume it just switches. Okay? Instead, we can check 1. That's positive. You don't need to know what e to the negative 2 power is. You just have to know it's positive. 4 times 1 minus 1, positive. Negative 1/2. That doesn't matter. It's still positive. When we're plugging in negative 1, we get positive, positive, which is positive. So we can make our guidelines. This should say that function's going up, then we're going down, then we're going up. F is increasing, F is decreasing, F is increasing. Because F prime is positive, then negative, then positive. So it means rel max at, if you set her thought negative 1/2, you are right, comma, we plug into f of x. We plug into f of x. we plug into f of x. We're not going to simplify. I don't feel like it. And a bunch of you just lost points on your test because of how much you want to simplify. There's no reason. You don't get more points for simplifying. You just probably get less. You get the same amount, or you can get less. The choice is yours. That's great. Done. I highly recommend you go try (1 through 14) on page 139. If you can do all 14 of those problems, you are in good shape. All right. You guys have a great night. Have a great day. I'll talk to you later. Bye.